In our last video session, we focused on the light-dependent reactions of photosynthesis. And effectively, when we did that, out of this master equation here, this equation that's an addition of many different equations, we actually took care of three of the elements. We took in the sunlight and the water. I didn't talk about this, but part of the process of the light-dependent reactions is splitting water, producing those hydrogen ions that it uses to pump, and then kicking off the oxygen. Those are the things that are part of the light-dependent reactions. We have left now the carbon dioxide, which we haven't dealt with yet. Remember that plants fix carbons into the biological world. They're the process of fixation of carbon on the land in the biogeochemical cycles. The fixation of carbon we haven't dealt with yet. That is in the light-independent reactions. Fixing it to produce the sugar. Taking that, the ATP that we generated from the light-dependent reactions, sticking it into the molecule of sugar. And so that's what we want to look at briefly next. The light-independent reactions of photosynthesis. Looking at this briefly, what we see is that the reactions in this particular part of photosynthesis make up a cycle, a circular motion of molecules. And then it's called the Calvin cycle after the individual that elucidated most of it, clarified most of it for us. What comes into this particular part of photosynthesis is ATP that we generated in the light-dependent reactions and some electrons. These are the things that we're going to need in addition to the carbon dioxide to ultimately produce our sugar. An important observation here is the fact that it is a cycle. What is going on here is, as far as design goes, we have discovered that cycles are very good ways to keep something going that you're doing on a continual basis. Let's say you're designing a car to rotate tires to move along the road. We can design a system that's, let's say we're trying to do something similar to the way cars are designed. We've got a piston, we push the piston up, put some air and some gasoline in there, ignite the puppy, that moves the piston. The movement of the piston we use to rotate an axle to rotate tires. But once we have moved the piston down, the question is, how in the world do we get the thing back up again? So that only goes in one direction and stops. So if we have another piston that is at the moment that this one is all the way down, another piston is up, we can have that thing fire and rotate the tires one more time. I mean, if we had 15,000 of these things, we could actually keep the tire going. Or we could be really clever about this and actually connect the two pistons together so that when the one piston is going down because of the firing of the gasoline, it uses some of its energy to push the other piston up and resets that piston so it's ready to be fired. You're not going to put all of your energy into the rotation of the tire. You're going to preserve a little bit of it to reset the other piston. So when the one piston goes down, the other piston is ready to fire. When that piston fires, it goes down, pushing, using some of its energy to push the first piston back up again. In this process, we can keep the process going. You don't have to stop every time you need to reset your pistons. It creates a cycle. Cycles are very efficient. You use some of your energy in the cycle. Rather than put everything into your product, you put some of the energy back into resetting the system. That's basically what's going on here. It's a system that would naturally just go in one direction and then stop. But if we use some of our ATP that we've generated to reset the cycle and start it over again, we can keep our cycle going. And roughly, again, not getting into any details, basically what happens here is as we move along this cycle, and what we're doing is transferring molecules from one molecule to another. We add energy to it. We pull in a carbon dioxide, stick it on. Every time we go around the cycle, we basically stick another carbon onto a molecule. Eventually, go around 3 times, we kick off a 3-carbon chain. Go around 3 more times, we kick off another 3-carbon chain. We put those 2 things together, we have a glucose molecule. So basically you turn your cycle around 6 times and you generate sugar in the process. So we've taken ATP from the light-dependent reactions plus electrons from the light-dependent reactions, added some carbon dioxide and pulled in carbon dioxide, and we end up building sugar in this process. Again, the details we're not going to go through at this time, just that you understand the basic cyclical nature of the process. That's photosynthesis, and now what we've done is we've accounted for the entire reaction in a summary form. The light-dependent reactions, sunlight plus water, gives us our oxygen. The light-independent reactions is the carbon dioxide being made into sugar. We can turn to aerobic respiration, which is an example of one of the ways that consumers, in fact, get energy out of organic molecules. And consider that for a moment. And the reason we consider this particular one is simply because most animals use this. We use this. So it gives us insight into how we have been designed. And here's the basic chemical reaction of aerobic respiration. Just like the one for photosynthesis, this is hiding a lot of complexity. There's a lot of molecules and a lot of steps in this process. But the summary is that sugar, glucose, plus oxygen from the atmosphere is put together and used to generate energy and carbon dioxide and water. And you might note that these 2 things kind of look similar. That in fact up here we've got energy plus carbon dioxide plus water gives us sugar and oxygen. We've got sugar and oxygen down here that give us energy, carbon dioxide, and water. It's the 2 equations flipped, basically. This is a cool design. God designed plants to put energy into organic molecules, and then animals are designed to take the organic molecules and get the energy out in a very much mirrored process. This allows animals to take advantage of the energy of plants, and plants actually to take advantage of their own energy to get energy out of those molecules. Aerobic respiration is a complex process, but central to this process is another cycle. We have a citric acid cycle here based upon one of the steps in it involves citric acid. And this is again a cycle which is efficient. Some of the energy of the cycle is used to reset the cycle so that it can be ongoing. Again, oversimplifying what's going on here, there's a portion of the cycle that is not, well, there's a portion of aerobic respiration that's not part of the cycle. It's called glycolysis. This is done in the cytoplasm of the cell. Doesn't have to be done in a special in a special organ or organelle. It's done in the cytoplasm of just about any cell can do this. And what's involved here is basically that glucose molecule with 6 carbons is broken in half, producing 2 3-carbon molecules, and a little bit of energy is generated in the process. In the process, you produce 2 ATPs. And you'll see the significance of that in a moment. It's basically a small amount of energy. Since this is done in the cytoplasm of the cell and doesn't need a special organelle, this could be done by virtually any cell in the biological world. This can be done by bacteria. This can be done by many organisms. It doesn't require the the oxygen that the cycle does. And so this can be done in anaerobic conditions. It's what's called anaerobic respiration, or the anaerobic stage of the aerobic respiration cycle. A little bit of the energy in sugar is derived in this manner. To get the rest of the energy, the pyruvate molecule, which is the 3-carbon molecule that's resulting from breaking your glucose, is brought into the mitochondrion for the citric acid cycle. So in the organelle called the mitochondrion, this is where aerobic respiration actually occurs. Remember, the mitochondria is that kidney bean-shaped organelle that has two major membranes, an outside membrane that gives the mitochondrion its outside shape, and then an inner membrane that's got lots of surface area folded, giving room for all of these molecules to have places to be located. In the process of aerobic respiration, when you go around this citric acid cycle, you extract 34 ATPs out of each glucose molecule. You only got 2 in glycolysis, the process that occurs in the cytoplasm. You get 34 inside the mitochondrion. So you get a total of 36 ATPs in aerobic respiration. It's 18 times as much energy as you do in the anaerobic stage, in the process in the cytoplasm. So a cell that has a mitochondrion can get a whole lot more energy out of glucose molecules than an organism like a bacterium that does not have a mitochondrion. And basically, I'm not going to go into any more detail than that, other than to show you there's a similarity between the aerobic respiration and plant photosynthesis that is obviously designed in the major system. There is a cycle in the center of the system, and it's extremely complex, and it's very efficient at getting energy out of the glucose molecule. Thinking now about the origin of that, of metabolism in general, we find that energy metabolism, like photosynthesis, aerobic respiration, and we could also see the same thing if we looked at fermentation, other processes of metabolism. All metabolic processes are extremely complex. And like in photosynthesis, where we understand only a small percentage of all of the steps, that's true across the board for metabolisms of all sorts. They are very complex. So complex that humans, with their great ingenuity, working over many years, have understood really very little of the entire process. And this complexity is far too complex to arise spontaneously without help of intelligence. We look at the world around us, we see some complexity automatically coming to be on its own without help, but it is nowhere near the complexity that we find in metabolism. Metabolism is mind-bogglingly complex, many times more complex than could arise by natural process. So this would suggest that naturalism has a very difficult time explaining the origin of metabolism in general. And remember, metabolism is something that every organism has to do. Every organism, even the simplest organisms, simplest bacteria, have a process of metabolism that's extraordinarily complex. In fact, the simplest bacteria, or maybe it's better to say, according to the fossil record, the very first bacteria that we have, they're chemosynthesizers using chemistry to get their energy out of chemistry. Those things are really bizarrely complex and very interesting, but many times too complex to arise by natural process. So metabolism looks designed. It looks like somebody has put it together. Plus, you add to the fact that each of these processes, as we come to understand it, are extremely efficient. Efficiency would be defined as the amount of energy we get out of the system If it's producing energy, we'd use that measure. How much energy we get out of the system compared to how much energy is potential in the system. If you could wring all of the energy out of the glucose molecule, for example, how much energy would that be? We divide into that the amount of energy we get out. The efficiency of aerobic respiration, for example, is very high compared to the efficiency of human-designed systems. The most efficient engine that humans have designed is actually the rocket engine. It's much more efficient than the engine on a car and that sort of thing. The most efficient engines and machinery that humans have devised is not equal to the efficiency of photosynthesis or respiration. It's amazingly efficient. We've tried to simulate it. When we try to simulate it, we get systems that work similarly, but we can't get the efficiency that we find in systems. This seems to be something that is designed with an intelligence greater than humans. In addition, I kept making reference to human designs in trying to explain how photosynthesis worked. I made reference to pumping water up into lakes and then putting them through the electricity generating dynamos. I made reference to the engines that are moving axles around. I kept making reference to things that humans designed, partly because they're astonishingly similar, but partly because that's what it looks like. It looks like something that some intelligence designed. It looks very much like human-designed systems. The ATP synthase is really rather wild. You've got these little hydrogen ions that go through. There's a circular motion that the molecule goes through, very much like the generator. It's almost mind-boggling how similar these designs are to human designs. It looks like, therefore, that metabolism itself is designed. And then, to make it really crazy, all this stuff happens in a chloroplast. A chloroplast is something on the order of a millionth of a meter in size. It is really, really small. We have simulated photosynthesis and respiration, but it takes very large sets of machinery occupying lots of area. I love the another kind of an analogous situation back years ago when we were wanting to toss the first spacecraft onto Mars. Scientists were really interested in collecting material on Mars and testing to see if life was there on Mars. I mean, there's all these sci-fi things that suggested that life was on Mars. So NASA was approached by scientists saying, hey, we would love to be able to use your spacecraft there, which already was designed to touch things and pick up things, but we want to analyze the soil on the Mars or the dirt on Mars to determine if in fact life was there or is there. And I said, okay, we can give you 1 cubic foot. We have enough room on the spacecraft. We could give you 1 cubic foot to create a laboratory to test for the existence of molecules. Wow, that's really amazing. They worked very hard, put nearly $1 billion into designing a laboratory that could fit inside a 1 cubic foot area, space, to test for, it turned out, I think there were 12 or 16 molecules that they could test for. And they thought they were doing a really good job. Well, they did a really great job. But if you think of the pineal gland and base of the brain, tiny little thing that's smaller than the end of your finger, It can test for 120 organic molecules every second for your entire lifetime. It's 10 times more capable of it can detect 10 times as many molecules, but it also extremely low concentrations, much lower than they could detect with this design. The design of biological systems on a micro scale blows human designs away. And this is over 500 chemical steps occurring in a tiny little chloroplast is an unthinkable design for a human being. These things look like they've been designed, but not just designed by a designer that's smarter, lots smarter than human beings. So what do we do with this information? First of all, our responsibility is to take this information and behave as creation priests. Our responsibility there is, first of all, to know God. The more we learn about photosynthesis, respiration, other forms of metabolism, the more we learn about this process of energy, the essential nature of energy, the power that's necessary in the universe for things to work, the more we learn about what it means for God to be powerful, to be all-powerful, to have control over all power. The more we learn about these things, the more we understand what it means for God to have control over all things. If He, in fact, is holding everything together, even on a micron scale, on an extremely small scale, He is holding things together. He's making things work. We learn about God's intimate control on even the fine scale of the universe. We learn about God's wisdom. Whoa, how complex, how amazingly well designed this is. It's such that if you're out there mowing, it struck me sometimes when I've been mowing my lawn, and here I am going across the lawn, this blade of grass has millions of cells with probably hundreds of millions of chloroplasts doing this amazing thing called photosynthesis. And I go along and go, just massacre these things. It's astonishing. This is happening all the time. And if I take a break, when my neighbor takes a break on mowing his lawn and we meet at the fence and we start talking about this, I sometimes can't help but go, this is amazing. What's going on here in these blades of grass? And my neighbor thinks I'm crazy. He says, what in the world are you talking about? And I start talking about this, and I'm able to share with him the awesomeness of the design. Both of us are looking for excuses not to go back to mowing the lawn, but we have opportunity to gain insight into the wisdom of God in creating this amazing complexity. His providence in putting all of that in place. Those plants are provided with this photosynthesis so that they have food. We are provided with aerobic respiration so that we can get food out of glucose. God figured this out a long time ago, but He's providing for our needs on a continual basis through processes that we're completely unaware of. And He's doing it on that incredibly fine scale. And then to think that there's no way that this process could occur naturally, it must have been designed. It shows us the incredible wisdom of the Creator, creativity of the Creator, and then the fact that we can understand it, or at least begin to understand it, the fact that it is there for us to figure out. He put it there so that we could understand something of Him. That's awesome. Why would a God with such incredible wisdom, with such incredible creativity, with such incredible power, why would He care about me? But He does. He desires me to know Him. And when I start contemplating all of this, it just causes me to fall into worship of Him and to bring others into that worship. And when I do, When I study the biological world and it causes me to be awed by God, when it increases my understanding of God, and when I can't help but fall into worship of God and bring others into that worship, I'm fulfilling my responsibility as a creation priest. And you can do the same thing. I would encourage you to keep on learning about these things in biology. The more you learn about God, get excited about what you learn, fall into worship of Him, and get so excited just to bring others, you are fulfilling your mandate of being a creation priest.